So glad to be here. Now I would like to link to what we saw also in the early morning session. What are the electrical engine, the architectures in the car? But I would like to take you also along the journey to a lower level, which are in many cases forgotten. So it's not only on the performance level where we are talking about, but we have to consider the whole system. So, okay. Seems to be a pattern also here that the slides don't show up. Okay. Let's start here. So I would like to remind you briefly on what is Infineon about. So where are we active? You see automotive is the biggest part of our revenue. And of course, the employees which we are having worldwide are working also in R&D worldwide, so we have to collaborate, and we by now have achieved the number 2 positions in automotive, but our strong foundation is power semiconductors, of course, and also security ICs, and exactly those three I will link together in my presentation today. And now, automotive, we have quite a long track record here, so we are the number 1 in these mainstream applications today, like powertrain, safety, body, and comfort. Number 2 in the overall market, more than 40 years experience, and I will show you one example. What does that mean, or what is the result out of that? This is the defect density statistics, which we plot regularly, and we are not only plotting it, but we are actively working on that through all our development, including the production chain. And you see, we have now switched from reporting on ppm levels. We are now to parts per billion, where we measure our defects, or to make it more tangible, probably you can have a look at this chart where you see we have our 24/7 production all the year long, and only the last 2.7 seconds of a year, that's where the defective parts come out. So this is an achievement, and we have to keep this in mind. Last year the figure was 4 seconds, this year it's 2.7, and we are keep on working to reduce it further. And this is exactly what we need also to keep in mind when we are talking about autonomous driving. What we have to keep in mind when we talk about electromobility, because these requirements also are applicable to these new domains. So just plugging in consumer electronic will work probably, but not for a long time. And now we see a lot of tech trends, and the CES, it stands for Consumer Electronic, by now is also dominated by automotive electronics. We see a new tech players like Dyson, so they're moving from vacuum cleaners into automotive and spending significant amount of money here. We see the new partnerships coming up, the innovation chain accelerates. We saw more changes in the last 4 years or 5 years than we saw in the decades before. And this is also a change which we have to adapt to. So, and to give you one example, if we look into the car manufacturing statistics, there's the talk about now peak auto, which means, okay, the number of vehicles will probably not further increase. Nevertheless, the content of the semiconductors, the semi-content per car will drastically increase, and we saw also figures on this one in the McKinsey presentation earlier today. And what makes it, I give you one example here, what are also new players. So we see about 50 new OEMs on electric vehicles coming up. And we also have to find ways how to address those new customers. Probably not everybody of those will survive. Nevertheless, we have to pick the right one. We have to bring them up to speed. And in the end, they will also be active on the market, still based on the requirements which I showed earlier. So we see these 3 mega trends. It's a little bit different. The first one, zero CO2, becomes real. This is a core belief. We see electrification is coming, clearly. We see also a driver becomes a passenger. This is what automated driving is about. But, and this is what we also have to keep in mind, a car remains a car. And what does that mean? Because this is the baseline, that vehicle is moving on the road. It's moving on the road. So electrical engineers' nightmare is that electrical system with all the voltage spikes and so on. And it has to operate and keep on operating for a long time in a reliable and safe and secure way. And if we look into this, and I now browse over a few milestones from the past, the driver becomes a passenger. It started long ago. The vision was already there. The technology, of course, was missing. And if you see electricity was supposed to be the driver, if you see 1957, this was an advertisement in the newspaper at that point in time. And today we would not say, okay, the electronic devices are embedded in the road. Today they are embedded in the car. But the drivers, highways will be made safe, no traffic jams, no collisions, no driver fatigue. This is exactly what we heard about the Vision Zero, reducing the fatalities on the road. So now it took quite a not so long time to see the very first autopilot in serious production. Guess when that was? 58. 58, that was the first advertisement of an autopilot in the car, in the Chrysler Imperial. And if you take your time and look into this block diagram, you see the very first indications of fail-safe design in this cruise control, we would call it today. Still, it was electromechanical engineering with some relays but that's it. And then it took a longer time, and I show you one. This was developed and set up here in Munich at the Bundeswehr University in Neubiberg, so across the highway from our site Campion, by Ernst Dickmann and team, so based on the Mercedes S-Class. And that car drove around Paris on the Boulevard Périphérique in 1994. It was a EU-based funded project. And if you look into the equipment of that car, yes, it was based on cameras, stereo cameras, gyro sensors, and a new compute architecture for the image processing, which was not readily available by Mobileye or whatever at that point in time. And it had no GPS, because the reasoning was you cannot rely on GPS. You are in a tunnel, you are crossing a bridge, GPS, you will have bad reception. Do not rely on GPS. So 2007 then, the GM Tahoe winner of that DARPA Urban Challenge had quite a more electronic content with LiDAR systems, with different ranges, 2 radar systems, mobile eye visions, GPS, and. And if you look at that car, there's one tiny detail. This is you see that on the top. This is the aircon. And it was quite a powerful aircon in order to get rid of the power dissipation caused by the electronic systems in the trunk. And if you now move on, 2017, this is the Chevy Bolt by Cruise Automation. They are doing this test rides in San Francisco today. If you look into the GM's self-driving report, you see they have 5 Velodyne radar, 21 radar systems, 16 cameras, ultrasonic radars, high-resolution data map, plus geofencing and stuff like this. And if you listen to Kai Vogt, what he says, these cars don't need drivers, no human mistakes, don't text while driving. This is new compared to the 50s. But the rest of the motivation, that still stays. Nevertheless, if you look into what is the range of that car, you take the 60 kilowatt hours battery, that range of the car compared to the non-autonomous drive version is reduced by 20% because of that electric equipment, 20% less. So this gives you, in addition, a nice budget for fitting more dedicated hardware with low power compute processors, new architectures like Paul Boutre yesterday explained. So this is a strong motivation. We have to keep this in mind. You can put an exascale compute probably into the trunk, but you need also a trailer for the power plant. And so now, if semiconductors now enter the driver's seat, we saw about this, let's say, this borderline between level 2 and level 3, and this is really where, let's say, the fun ends and the serious work starts, because you will definitely need to take into account that the driver isn't there. And it's also not realistic to assume that the driver wakes up, let's say, twice a year and takes over control in a very, let's say, skilled way in the most critical situations where the system is approaching its boundary conditions, in icy conditions or whatever. So that driver probably will be as trained as my grandmother, and you cannot rely on, let's say, it's just for giving away the liability for the subsequent crash. So this means if you look into the building blocks, still this drive layer will remain. This is where a car remains a car, the braking, the steering, the suspension, that means needs to work. The environment sensing, fusion data comes on top of that. And then there's the decision making, human-machine interface, but all pulled together by safety considerations, including all layers, and again also security. And this has to be taken into account when setting up the system right from the start, so down to the low-level architecture, down to the component level. And so you will have many sensors, you will have that control algorithm software instance, and this will be specialized sensor processors. We heard about one for the smart eye just recently. You will have the sensor fusion, you will have central gateways, and you will have the actuators. And on all these levels, these functional safety considerations plus the security considerations have to be designed in right from the start. You cannot piggyback that on top of the system later on. So what does it mean? The semiconductors then learn to drive. Probably today they are in the state of a 10-year-old, so probably. Still some way to go until they pass their driver's test. So you have that gigantic processing. It needs to be still safe and secure. Like in the human brain, you have different layers of processing. You will also have that in the car. You will have DSPs, GPUs. You will have safety controllers like the Oryx in there to supervise that system. You have that also on the communication layer. You need power supplies which are working under all conditions or have also backup capabilities. And you have to put this together. And there are some, let's say, layers or areas in the car where machine learning can bring benefits. We see this in, let's say, in the environment interpretation and processing of the radar, LiDAR, and the camera signals. Fusing that, of course, machine learning offers great new opportunities here. We saw that. Also, when it comes to environment modeling, and then predicting trajectory planning would be then the next one, and also the route planner. This is where AI comes into that. So this is not just one single processing unit doing all these AI and machine learning. It will be also in different parts of the overall system, and it calls also for dedicated solution, dedicated hardware accelerators to do so in the most performance, cost optimized, power consumption optimized way. And now, what does it mean, pass the driver's test? So semiconductors pass the driver's test, and we see there is this performance, safety, and robustness challenge, and it's not only on the very upper level, it's also, if we look, for example, in the high voltage inverter architecture, where we have low voltage domain and high voltage domain, and there must not be let's say a fail mechanism so that these domains get into contact with an uncontrolled way. This has to be detected, and if you have torque vectoring, for example, in the electric powertrain, also changing, let's say, or having an uncontrolled way of control between the motors on one axle or two axles will lead into an uncontrolled state on vehicle level. So motor position, motor temperature has to be measured constantly, has to be taken into a part. You need to have that decision path, that control path, and this is on the actuator side. You also have it on a system like electrical power steering. So, and now we are moving from, let's say, level 2, we heard it, until up to level 3, we move from fail safe into fail operational. Fail operational means even though the system or components fail, the system still has to work. Probably with less performance, but it still has to work. Okay, the simple way would just double everything. Double battery, double, let's say, 6-phase motor, okay, which works also. You put just 2 on them and so on and so on. Probably not the wisest decision to do in terms of cost. So there are more clever ways to do this, both all again on the level sense. So we put 2 separate dies in one package to have that diversity there. So we have multi-core lockstep processing. And we also have a multi-phase e-motor control on the power supply path, and we also have a specially designed motor which also works with reduced core if let's say you have a short circuit in between. So and this has to be designed in right from the start while still keeping in mind data security. So if the car is spammed with some let's say messages from the outside, it's not controlled, then we can talk a lot about functional safety. We see security as a prerequisite for safety, and this new ISO 21434 will exactly push us all into this direction. And we have to work on that one to deter any hacker attack from the car which is connected through multiple ways in future. So any interface of that connected car is a potential point of attack and has to be protected, let's say, with state-of-the-art or even beyond state-of-the-art technology. So deter, detect, defend, and this to be done on the interfaces, the gateways, the networks, and the processing is a challenge and has to be, again, designed into the system right from the start. So we are working on that. So Aurex microcontroller, we are collaborating with major suppliers here and providers also on the AI platforms. But again, just one takeaway, please. This is not everything. We have to break it down really to the component level to have fallback also on if the CPU fails. So the liability change. And I want to close with this one. Today we have the product liability that lies with the manufacturer for the product properties, and the driver is liable, okay, to not drink and drive. So keep in the state you can manage the car. Tomorrow that will change. So there is no driver, there's a passenger, and the product liability will be there. The product property, the behaviors is going to be changing over time. So the car comes off the assembly line, it will be a different behavior a year later or 2 years later. So how to control this, how to make sure that it doesn't evolve into an unwanted direction. Product updates, how to control this. So this is a huge challenge while still guaranteeing data integrity, data security, infrastructure liability, what happens if wrong traffic signals are transmitted towards the car. So who is liable if something goes wrong? And still this calls then for, we saw the fragmented landscape today, Joe Nataro of ON was presenting, and we have to pull this together, though there's a lot of challenges also in the localization to put a car on the road in India, in Europe. So what needs to be the difference in the behavior? Will we have different platforms all over? So we have to pull this together. We have to have standard driving situations, so who is independently testing the behavior of the car later on. This is a challenge. Today we see also public authorities not yet in the state, let's say, or knowledgeable state to really be able to test it in a way. So who is going to do this? Who is going to certify the cars there? So lots of exciting things to do. Really looking forward. It's exciting roller coaster time for engineers, and we see this. Many people are really eager to participate in this ride, and so it has started. Yeah, semiconductors are the key to this. Without semiconductors, it will not come. And but we have to collaborate across the whole value chain. Thank you very much.